Okay, so now we're going to continue on from the example in the previous video. Namely, we had this function f of x, and we walked through in the previous video how we identified some of the key properties that we need for the skeleton graph, which is shown here. So we got a y-intercept, horizontal asymptote at y equals 1, a vertical asymptote at x is minus 2, and x-intercept at 5, and we have a hole at x equals 2 where the common 0 was for the numerator and the denominator. And so to fill this graph in, we can set up a sign chart. And so for the sign chart, we're going to just set up a number line, and on this number line we're going to mark each of the x values where one of these key properties occurred. So for example, at x equals 5, we had an x-intercept, so I'm going to put a 0 over x equals 5 to denote that the function is equal to 0 there. At x equals 2, I'm going to put a h over that value because the function had a hole in the graph at x equals 2, and at x equals minus 2, I'm going to put a VA over that value because the graph had a vertical asymptote. And now for each interval, so I've got one interval here, a second interval, a third interval, and a fourth interval between x values where one of these features happened, we're going to pick a test value. And it doesn't matter what x value we pick, I just want to pick any x value less than minus 2 in the interval 1. So for example, x equals minus 3 would suffice. In the interval between x equals minus 2 and 2, I can pick an x value, a test value such as x equals 0. Over here, I'm going to pick a value between 2 and 5 such as 3. And over here, I'm going to pick x equals 6. And for each of these test values, we're going to check to find out what the sign of the function f is. So starting on the left, the test value at minus 3, I can plug into f, or the reduced function for f, either one, and evaluate it. And we can check here that this would actually give us 8. So that means the function is positive for all of these x values below minus 2. And for the other test values, f equals 0, which is in between minus 2 and 2, well, that's where the y-intercept is, and we know that is minus 5/2. So that's less than 0. So we put a negative sign above that test value. At f equals positive 3, we get minus 2/5. That's negative. So I'm going to put a negative sign here. And the last test value that we need to check is something bigger than x equals 5. So for example, at 6, we get 1/8. So we get a number which is bigger than 0, positive number, so I put a plus here. And now in the graph above, the skeleton graph up here, I just fill in a portion of the graph that either sits above or below the x-axis. So since I know that when x is less than minus 2, the graph needs to be up here, I'm going to fill in that portion up here as opposed to down here. So this gives me a piece of the graph that looks like that. Okay, so it's above the x-axis. And in between minus 2 and 0, so between this region, I know that the function is negative. So that means the graph down here is negative, and it goes and passes through the y-intercept, passes through the hole, and then passes through the x-intercept at x equals 5. And down here, the behavior is that it's going to keep going down to negative infinity as we get closer to the vertical asymptote on the right. And then lastly, for x values that are bigger than 5, we see that it's positive over here. So the graph continues and flattens out as it approaches the horizontal asymptote. So this gives us a pretty, this graph is pretty rough, but we get the general shape of the graph. We see the intercepts and the end behavior and the behavior near the vertical asymptote. So we see all of the key properties of the graph that we would hope for it to reflect.